Hello, everybody. I will start today with the topic which is called freedom from interference. It's a very simple problem, but to solve it, it's really very challenging when it comes to the different software components that have different ASIL levels, and they are sharing the same memory space. So today I will basically speak a bit about the challenges under the different multi-core architectural approaches, and then I will illustrate the challenge that we are trying to solve during this webinar, which is freedom from interference for the multi-core architecture. We'll see practical approaches how to achieve this freedom from interference, and then we will see the pros and cons for each approach that we illustrated. And after that, you can ask your questions and we could follow up regarding your questions later on. So when it comes to the multi-core architectural approaches, basically the system architects, they are very creative in this area. So you have basically more than one core, and you have software, and you have to map this software components and the real-time operating system and different software components basically on the hardware. And if you look at the slide from the left side, this is one strategy that's called full AutoSAR. And inside this strategy, this system architect decided, okay, we have the safety operating system and basic software for the ECU. And after that, I will put the RTE or real runtime layer that communicate or facilitate the communication between the different software components. And then I will divide basically the cores based on the type of the software component. So if it's AutoSAR software component, I will dedicate 1.5 core for the AutoSAR software components, and for the ADAS software components, I will dedicate the rest of the cores. So this is basically one strategy that the system architect could go through it or decided for it. And the next one, which is the microcontroller partitioning. And inside this microcontroller partitioning, basically there is a kind of separation between the AutoSAR and the ADAS applications. So for the safety OS and for the runtime layer and for the AutoSAR software components, all these components basically will be run on one microcontroller, and for the rest, which is the Linux operating system, for example, and for the ADAS applications, it will be run on another microcontroller, and then there is one communication, or maybe more than one communication between these two microcontrollers, and this is basically the partitioning based on the microcontroller. Or some system architects decided go for the core partitioning, and for this core partitioning, basically they dedicate 2 cores, for example, here in this example for the ADAS, and for the safety side, they dedicate 1 core. Or some system architects as well decided for the 4th one, which is a hypervisor methodology, and in this basically they use a hypervisor, and they use more than one operating system, and they let the hypervisor monitor basically these 2 or more operating systems for the for this approach. And basically this for each approach, definitely there is pros and cons. For example, for the microcontroller partitioning, in terms of cost, this is the highest, the most expensive solutions that you could go for example. But the point here, or what I'm wanting to say is, regardless from the multi-core approach that you already use on your system, once the software components are gathered together and they are sharing the same memory space, this could lead to the problem, which is the freedom from interference, or how can I guarantee this freedom from interference concept once I gather together basically more than one software component that have a different ASIL level, but at the same time they have access to the memory. And if you look basically on the left side, you will see here you end up with the safety requirements, and the safety requirements is translated to the safety software components, and you have as well non-safety requirements, and for this non-safety requirements, it's mapped to regular or QM components. And in order to minimize the cost, basically you combine both together, the safety related components and non-safety related related components. And you want to make sure that for higher safety related components, you don't want to get any kind of problems that could cause from lower or software components to the higher software components. So basically, if you look at the right-hand side in this diagram, you will find basically this is kind of a simple schematic for multi-core applications. So you will find here we have like 3 cores for core number 1. We have 2 applications. For core number 2, we have 1 application, and there is 1 application running on core number 3. And if you look at the memory, you will dedicate basically memory segments for every application. And this is really good. And one application has its own space or memory space, and the application could use only this memory space. But basically, this is it's difficult to achieve because for every application, you could use wild pointers, and this wild pointers basically it could jump to some memory space that's not authorized to access to, or this pointer try to write to read memory only memory, for example, and this could really cause big runtime problems. And to achieve such a solution or to tackle this problem, or to achieve the freedom from interference concept, one could decide to go for the memory protection unit or MPU. MPU, it's a hardware module that you need to configure, and after the configuration, basically it regulates the access to the memory. So you configure it, and after that, once there is unauthorized access from one or more application to the memory, so this the MPU handle it, and it generate interrupt. And if you are using a runtime operating system for your application, which is most probably the case, so you have to handle this interrupt into your application. So this is basically the first solution to regulate or to guarantee the freedom from interference into your software applications. Or you could go to the second solution, which is the safety checker. So safety checker, it's basically a software tool that can guarantee the freedom from interference as well. So it's on the other side from the first solution, which is the MPU. It's a software solution, it's not a hardware solution. And basically, this is how it works. So the safety checker, it takes your source code from different applications that you already developed into your software stack. And as an input as well for the safety checker, you will get, or you have to configure the safety checker, and you have to define basically the access rights and the safety classes that you are using. And you could as well integrate archives from different third parties that they already use the safety checker in their applications. And the safety checker take all this as an input and then generate access violations. And these access violations, basically, it's unauthorized accesses from different applications to the memory based on what you already defined into your configuration file. So this is basically how the safety checker in a simple form works. I already prepared some simple demo for this tool. So basically here you will find 3 files. I could say 3 different ASIL level software components. It's called file 1, which is I assigned ASIL A. I wanted this software component to be ASIL A. And for this software component, it has it's very simple. So it has 1 structure and 1 function that returns this structure or return reference to the structure. And for the second component, I want it to be like ASIL B software component. And inside this, I developed 1 function, and inside this function, I called function number 1. And for the third component, I assign ASIL C as safety level for this component, and I defined function 3 inside it, and I called function 2 from this. So this is basically the flow or the software that I have. It's very simple, but it illustrates basically the problems that we're facing which is there is accesses from one software component to another, and I want to make sure that there is no bad accesses or there is no violation based on the rules that I already put for the safety checker. So in order to guarantee that there is no violations for the rules that I already put, I have to first configure the safety checker. And the configuration for the safety checker, it's only one file that contain different classes, and inside these classes, basically you are putting the rules for your software. So for one class here, you could define basically what different software components with different ASIL levels could do or could have impact for each other. So for example here, ASIL B software component can execute only ASIL A. It's on the right here. It's basically like Linux. So you will see it's either execute or read or write. So this is basically the writes that could be executed from the source to the destination. And for the second part here, I am describing, okay, as a source, ASIL C component can execute and can read and can write to the ASIL B. So basically for ASIL C, it can do everything to ASIL B software components. And for ASIL C, it can only write to ASIL A. So this is basically how I describe the different ASIL software components and the writes between the different ASIL software components. The second class that's inside the configuration file for the safety checker is the class which describe basically the software that you are having. So as I mentioned here, we have like 3 files or 3 software components, if I may say, and I'm describing here basically what is inside the files, and I'm assigning an ASIL level to this file. So I would say, as an example, the software component or the software file, which is called file_3.c, everything inside this file is ASIL C. And for the second component, everything inside it is ASIL B. And for the third file, which is file1.c, everything inside it is ASIL A. And inside this name mask, basically, you could define asterisk. Asterisk means everything inside this file, or you could define, for example, structure, or you could define function. So you could define basically whatever you want according to the name mask that you already give inside this class. So basically, you could assign inside this file3.c, you could assign, for example, a structure that's ASIL C and a function that's ASIL B. So this is basically doable with these configurations. And once I already configured this configuration file for the safety checker, so the safety checker run for your whole software based on the configurations that you give, and then generate the output. And this is basically a snapshot from what the generated report from the safety checker is. So as you can see here, it gives you a matrix that describes basically the writes from the source to the destination in a matrix form. So this gives you a kind of iBird for whatever software components writes from one component to another. There is one section inside the diagnostic report as well, which it describes basically your software. So this is basically, it says everything inside file 3 is ASIL C, and the safety checker already used it during his check. And then this is basically the most interesting part from the generated report, which is basically the call graph. So the safety checker generate a call graph for your whole software, and inside this call graph, basically you could see there is some checks here that's done from the safety checker, and if the check is okay, that's fine. And if the safety checker find a violation based on the rules that I already described or give or configure for the safety checker, so this could be highlighted in a different color, and it says here it's access violation. And if I could dig deeper inside this access violation, it says check access for reading my struct, which is a structure, and it's has ASIL A from F3, which is a function, and which is ASIL C. And if you go back here and you see basically this violate what I already described in terms of accesses here. So ASIL C can only write and cannot read from ASIL A. And this is basically detected with a safety checker, and it's highlighted as an access violation here. So basically inside this presentation, we see two solutions for the freedom from interference concept. So we see the memory protection unit as a solution, and we see the safety checker. And here you could basically check what are the pros and cons for every solution. So in terms of configuration effort for the MPU, it really takes big time to configure the MPU because it's really a complex component, and you have to have like a big expert how to configure this MPU. But for the safety checker, it's only just one file that you need to basically configure your software or describe your software, and then run the safety checker for the whole software stack. And if you think about, okay, do I need a hardware or not to use this tool? So basically, you definitely need the MPU inside your microcontroller in order to use this solution. So it's really kind of a hardware dependent solution, but for the safety checker, it doesn't need any kind of hardware in order to run it for this for the whole software stack that you have. And if you think from the process point of view, it fit as well for the safety checker. It fit into your agile methodology because you could run it for a part of your software, for your whole software, whatever you like. So it fits into your agile methodology. But for the MPU, basically, it will be difficult to be fit inside the agile methodology because you have to integrate your software, and you have to then after the integration, you have to turn the MPU on, and then you will be surprised with the big number of violations that's already catched by the MPU. And this is basically a big problem because it could take a lot of time in order to investigate what are the violations and how to mitigate these violations. And from the testing perspective as well, it will be difficult to automate such tests for the MPU. But for the safety checker, basically you can automate everything. So this is definitely a time saver. And as well from the code coverage, it will be difficult for the MPU because you have to stress the system and put it in different states in order to hopefully get some violations that you don't like to see in after you already deployed your system. But for the safety checker, it's really the code coverage. It's very high because you have full flexibility what kind of modules that you want to run the safety checker on, and this is basically reflected onto a higher code coverage. And based on all these points, you will be impacted with the time to market strategy. So it will be a big high risk if you use the MPU, and you will be surprised with the number of violations that could be generated after you integrate your software and you start to testing it. But it will be low risk if you use a safety checker, definitely. Though it's what I don't want to say here is the safety checker is not a totally substitution for the MPU. So the idea with the safety checker is to minimize the number of violations that you will get after you already deploy your software and turn the MPU on. So this is basically the idea behind the safety checker. So it really minimizes the number of violations after the integration of your software and turning the MPU on. So this is basically for the safety checker. I would like as well here to give you kind of overview about our full tool set. So basically we have like the compiler, which is the ASPICE level 2, and this is definitely could help you into the qualification against ISO 26262 and other standards as well. We had a previous webinar about the embedded profiler, and you could find it onto the Hitex profile website. And we have as well a performance libraries that could support you onto your ADAS applications, the embedded debugger, which is a cost-effective solution when it comes to debugging your software. And we already saw today the safety checker, which is a static analysis tool that basically checks the violations based on ASIL levels. and the compiler qualification kit, which could help you to qualify your software against ISO 26262. So this is basically the kind of ecosystem that we are offering, and we are really believing in the ecosystem and not only one tool that could fix everything. So we are supporting you in a different by giving more components or giving more tools that could help you when it comes to developing multi-core software-related applications in the automotive space. The next webinar, it will be talking about the compiler qualification kit. This is basically one product from Tasking, and it helps you to streamline your ISO 26262 certification process. So this could help you to certify against ISO 26262. And it will be on 12th of September at 11 o'clock. I would like as well to highlight the after lunch seminar. So we will have with Hitex the after lunch seminar. It will be and it will take place in three locations. So Karlsruhe, München, and Hanover on 11, 12, and 13 of September.